Well, good morning to all of you to the very first session of this subject, fluid mechanics. The course is fluid mechanics. So at the outset, I like to tell a few words to introduce the subject, after which I will describe the course contents. Now, the subject fluid mechanics as such is not unknown to you. I feel so because a part of this subject you have already read at your school level and also at the first year level of your engineering course. Now the term fluid literally means the things which can flow, and it technically encompasses liquids and gases, these two states of matter that you already know. The subject fluid mechanics describes all the physical laws that govern the flow of fluids and gases and ultimately help us to recognize the causes and effects of fluid flow through the determination of characteristic parameters like pressure field, velocity field in a fluid flow, along with the different properties of the fluid like density, viscosity, and mainly a interrelation between these two. And in different situations, not only in the flow of fluid but also in cases when the fluid is at rest. This is basically the subject fluid mechanics deals with. Now the importance of the subject, I think, is apparent. This is because probably you cannot find out a single phenomena in the universe which is devoid of fluid as the working medium or substance or flow of fluid. For example, if in our basic existence or survival depends upon breathing in and out, the circulation of the blood, these all depend on the principle of fluid flow. We can imagine that we are living in the ocean of fluids, that is air. The pressure that is exerted by the air on us is also governed by the laws of fluid. If you go up, you know that we have experienced less atmospheric pressure. These are also laws of fluid. If you seek engineering applications, you will see that starting from very simple engineering application by sprinkling water in a lawn, transportation of water, different fluids, oil through pipes, down to the high-tech areas, that is the technology of submarine under deep sea water, propulsion and launching of aircraft and space shuttles, all depend on the principle of fluid flow. So therefore, I feel it is needless to emphasize the immense importance of fluid mechanics, not only in the field of engineering but also in the field of daily life anymore. Well, at the same time, we know that fluid mechanics is a classical subject like physics. So if you want to find out its origin, probably it dates back to the discovery of Archimedes, discovery of buoyancy by Archimedes. Well, since then fluid mechanics have been developed by a number of scientists, starting from Newton, then Lagrange, then Euler, then Rayleigh. They are the classical scientists who first made much contribution to its development. Initially the fluid mechanics, the subject came up as the subject of other sciences based on natural observation backed up by physical theory and analytical methods. But afterwards it was found by engineers that many of the happenings, down to earth happenings, cannot be corroborated by theory, analytical theory. So there becomes a widening gap between the experiments and theory. Then engineers put their enormous effort to carry out experiments to develop empirical rules in the field of fluid mechanics, from which the birth of classical hydraulics came up. This gave the birth of classical hydraulics. These are the terminologies probably you know today as your popular knowledge. The classical hydraulics came up. But this continued for a long time, but in the beginning of this 20th century, scientists felt that strong theories are required to bridge up the gap between experiments and the theory. That means what is found from the very simplified theory cannot explain all the phenomena in practice. So then the famous persons like Prandtl, Nicoretze, Taylor, there were several others who developed fluid mechanics and its theory tremendously and tried to build the foundation of fluid mechanics on a very rigorous and rich mathematics. And what we find today from a development from the field of classical hydraulics to the computational fluid mechanics, which is probably, as you know, the name is the most modern and the burning topic of the day. This way the fluid mechanics has been developed. But if you see through these developments, you will find a common thread running between all these, which is the essential or the basis or the basic principles of fluid flow, which will be brought home effectively in this course. And I hope this course will give you this primary level understanding so that you as an engineer can apply the principles of fluid mechanics to engineering design and also can understand any advanced level course of this subject. Well, so now with this I will show you the introduction, the contents of this course package. This course package consists of this fluid mechanics, I think all of you can see. Well, a first level course, this is a first level course. First, it starts with introduction. Now, this does not give you an elaborate description of all the course content. It gives you in terms of the overall, that is the broad topic, that introduction, and this will include also fundamental concept. This may include 3-4 lectures. So, it will go like that, part 1, part 2, part 3 of introduction. Then we will come to fluid statics, which will cover all the aspects of fluid statics. Then we will go to kinematics of fluid. So, lecture schedule will go like that. So, fluid statics will take few lectures which will go like that. Fluid statics part 1, fluid statics part 2, fluid statics part 3 like this. Well, then kinematics of fluid, number 3. Then we come to the next topic is this for your exposure. I just tell you conservation equations for fluid flow. What are the conservation equations that govern the flow of fluid? Then fluid flow applications. So, details of these will be available in your leaflet or the course curriculum that have been given to you. Then number 6 will be viscous incompressible flow. Number 7 will be application of viscous flow through pipes. Then, well, number 8 will be principles of similarity, which is very important in the field of experiments. So, one cannot do anything without the principle of similarity. If you want to predict the performance of any system in practice, in field, you will have to do the model experiments in laboratory. But the very pertinent question comes, under what condition the model experiments have to be done? What should be the altered scale factors in terms of all the variables, not only the geometrical shape of the model, which will allow you to predict the results from your laboratory test for that of the actual system in practice. And you remember that is a very important subject at this level. Well, so principles of similarity, then flow of ideal fluids, then number 10 flows with a free surface, number 11 is few unsteady flow phenomena in practice, number 12 and 13, last 2 lectures, introduction to laminar boundary layers. This will go to little advanced stage, and then introduction to turbulent flow. Well, after that I will tell you about the books. As you know, the subject is a classical subject, there are a number of books. So therefore, I as a teacher do not feel that always one book or 2 books you will follow. You can follow any book which covers well the syllabus or the course curriculum. You can find any book, but book reading is a must for your concept. Only teacher's lecture will not do, because you will have to read books, you will have to solve problems from books. There are plenty of books, any book will do, but a few such good books I am just mentioning, textbooks. Well, the first book is by me, Shom and G. Vishwas. I have already told you that Professor Vishwas is from IIT Kanpur. This book, this was written based on our teaching experience at IIT Kharagpur and IIT Kanpur. So you can see this book is in market. This is published by Tata McGraw-Hill. Then Fluid Mechanics by Frank M. White, which is again a very good book. This is published by McGraw-Hill, which is widely followed in American university. But this book you will get in library, but you cannot purchase probably. This is costly. So this book you can purchase. Other books are Elements of Fluid Mechanics by Sheshadri and Patankar. Another book also you can see, very well-known classical books in the field, that is also by McGraw-Hill, that is Mechanics of Fluids by Irving H. Sims. So these are the textbooks recommended for this subject. Well, now after this, let us try to concentrate on the subject from the beginning. What is fluid, what is meant by fluid from the viewpoint of mechanics. How do you define fluid from the viewpoint of mechanics? The very first definition of fluid from the viewpoint of mechanics comes with its distinction in its behavior from that of a solid. If we apply a tangential force or a shear stress to a solid, our common experience, or we have already read, we see that solid undergoes a definite deformation. Even if the shear stress exists, the solid may be under equilibrium with a particular deformation, shear deformation. All right? And if we lift up the load, then what happens? Solid may or may not regain its shape. It may completely regain its shape or may not completely regain its shape. Within certain limit, you know, if the stress is relieved, the solid regains its shape. Or beyond certain limit, solid may not regain its original shape, partly its original shape. But in this respect, fluid makes a very distinguishable character, behaves in a different way, that if a tangential force is applied to a fluid body, it goes on continuously deforming. You cannot make fluid at rest. Fluid goes on deforming continuously. Let us see this in a very simple manner, that if we make a solid body like this, if we just see a solid body, if a shear stress is applied on it, let tau is the shear stress, the solid body may undergo a finite deformation. Let the deformation is denoted by this angle alpha. And the solid body can resist the shear stress at static conditions, static equilibrium, with this deformation. Whereas, if we have a fluid flowing, any fluid flowing, let this is the fluid body, this is the fluid flowing, streams of fluid flowing. So, if a shear stress is applied on the fluid element, you just consider a fluid element in the body, you will see this line, for example, linear element, this goes on continuously deforming fluid. If we try to identify a fluid element, this goes on continuously deforming. That means if you just see a linear element 0, 1, it goes on 0, 2, 0, 3, 0, 4 like that. That means a continuous deformation takes place. And as such, this continuous deformation constitutes the flow. So therefore, we come to two very important conclusions from the mechanics point of view, which differs fluid from the solid, that solid can resist the shear force or shear stress under static equilibrium condition with a finite deformation. And it can regain its original shape or partly its original shape when the load is relieved. Whereas fluid goes on continuously deforming, which means that fluid resists tangential force only under dynamic condition. It cannot resist tangential stress under static condition. It resists the tangential stress, definitely it is resisting. But while resisting, it goes on moving continuously. That means a continuous deformation takes place. And another very important characteristic is that if you relieve the load, take off the load, fluid cannot come back to its original shape. Except a very special case I will mention, which is beyond the scope of this book. All books write like this. That's why we tell that fluid is a zero memory substance, that it forgets its memory, whereas solid is not. Within certain limit, it has perfect memory. That means if load is removed, it regains its full memory. It comes to the original shape, where the fluid cannot have, except a certain class of fluid known as viscoelastic fluid, which possesses partly elastic property, which is a very special class of fluid known as viscoelastic fluid, which is beyond the scope of the present course. But except this viscoelastic fluid, all fluids have zero memory behavior. That means when the load is removed, the fluid cannot come back to its original or even partly the original condition. So these two distinguishable features makes it different from that of a solid. This is the basic difference between a solid and a fluid. Now you know that in case of solid, you have already read, this stress produces a strain. That means a deformation, and there is a definite relationship between stress and the strain, and that relationship is known as constitutive equation. You know within certain limits, generalized Hooke's law tells that stress is proportional, linearly proportional to the strains. All right. Similar constitutive equations for fluids are there, where stress is not related to strain, but related to what should be? If there is a continuous strain, that means continuous deformation, so therefore it should be related to the not the variable strain, the variable will take its time rate, because there is no definite strain. So you cannot define a definite strain. For a solid we can define a definite strain. So it can resist the stress under static condition with a definite strain. So a relationship exists between stress and strain, which is the constitutive equation of the solid. Similarly, the constitutive equation of fluid relates stress with rate of strain. That is the basic difference in the constitutive equation between solid and the fluid. That means fluid, it is the rate of strain which comes into picture, because fluid goes on deforming continuously under the action of external forces. Okay. Now, after this, I will tell you another very important concept before proceeding further, that is the concept of continuum. Okay, you write concept of continuum. What is meant by concept of continuum? Well, or continuous medium, either of the continuous medium. The two terminologies are there, continuum or continuous medium. What is meant by continuum or continuous medium? Very simple. Now you see, in the description of matter, what we do when we define the property or any parameters, for example the pressure or velocity or any property, the temperature, well, we define it as a continuous function of space within the matter at any time. Or we can define it as a function of space and time. So at any time we define the property or these parameters as a continuous function of space within the matter. So what does it assume basically? It assumes that at each and every point in the matter there is a molecule, because all matters are composed of molecules. Then only the property can be defined as a continuous function of space in the matter. There is no discontinuity. Though we know the matters are composed of molecules and there will be a gap between the molecules, but we always assume while defining this way the properties that always there is a molecule at any time, at any point in the matter. That means the gap between the molecule is almost zero. In fact, this is highly true for solids and liquids where the molecules are closely packed, and we can consider this as an assemblage of a single substance. But this is not so for gas, as you see, and if the gas pressure is very low, this is not true. But under ordinary conditions, we can find that for gases also molecules are very closely packed. You know the number of molecules within a certain volume of gas is given by Avogadro's hypothesis. If you recollect the number of molecules, probably if I recollect the Avogadro hypothesis, it gives 6 point something like 023 into 10 to the power 23 molecules. Just you see, this is of course at standard temperature and pressure per 22.4 liters of gas. So at that standard condition, you can find out a molecular density of approximately 2.7 into 10 to the power 25 molecules per meter cube. That means divide this by 22.4, which gives per liter, and multiply with 10 to the power 3. So this figure comes, this is a figure usually we refer, approximately 3 into 10 to the power 25 molecules per meter cube, which is so high that under ordinary conditions we can also think that gas molecules are so closely packed that we can neglect the distance between the molecules and can define the properties or any other point functions of the fluid as a continuous function of space within the matter. This is precisely the concept of continuum. But at the same time this comes into picture, is it so that always concept of continuum or the continuous medium will be valid? For example, if you go on ratifying the gas, that if the pressure of the gas goes on decreasing continuously, we know that the distance between the molecules increases. Well, and the cohesive force between the molecules decreases. So whether the continuum will be valid or not? Yes. That pertinent question was answered by a scientist, and he found out a criteria based on which the concept of continuum will hold good. And this criteria is based on the distance between the molecule. You know, the distance between the molecule is well characterized by mean free path. What is the definition of mean free path? That is the statistically average distance the molecules travel between two successive collisions. That means if this path could have been 0 theoretically, that means molecule is always under. At any instant of time, there is in collision. That means there is no distance between the molecules. So lambda is not 0. It has got some value, that is the statistical average distance molecules travel between two successive collisions. Now the measure of lambda relative to the characteristic dimension of the problem defines whether your continuum will be valid or not. That means you want to investigate certain phenomena in a system whose characteristic dimension is the order of the molecular dimensions. Definitely, from very common sense, even a schoolboy can tell no, the concept of continuum will not hold good, because we will hardly have a molecule within the system. So therefore it comes by the concept of relative magnitude of this mean free path with the characteristic dimensions of the problem. So characteristic dimension of the problem will vary from problem to problem. For example, it is a case of pipe flow, it will be the diameter of the pipe. It is a flow past a body, some dimension of the body. So characteristic dimension of the problem will depend upon the problem. Now if we recognize lambda as the mean free path, well, lambda as the mean free path, lambda as the mean free path, well, and L is the any characteristic dimension of the problem, characteristic dimension of the problem, that depends upon the problem constant, that is the physical problem. Then the relative magnitude, this ratio lambda by L, is known as Knudsen number, K-N-U-D-S-E-N, Knudsen number. The name is after the name of the scientist who first, Knudsen, please. Well, Knudsen number, lambda by L. Well, now this lambda by L serves as the criteria for the concept of continuum. That means when lambda by L is less than 0.01, then the concept of continuum is valid. Continuum concept is valid. That means continuum is valid. Continuum is valid. Well, you must know that when the continuum, the departure from continuum, that when 0.01 is less than lambda by L, it is greater than that, but less than 0.1, then we call it as slip flow. Then the concept of continuum will not be valid. From 0.1 to 10, that lambda by L less than 10, the flow regime is known as transition flow. What is that transition? That is transition from slip flow to free molecular flow, where the most realistic case will be to analyze the behavior of individual molecules. This is the case when lambda by L greater than 10, that this is the transition flow from slip flow to free molecular. So when lambda by L is greater than 10, the flow is known as free molecular flow. However, our course does not consider this. We will be only within this regime, continuum or the continuous medium. So in all ordinary cases of fluid flow, ordinary cases means ordinary states of the thermodynamic states of the fluid medium, the concept of continuum is well valid. That is lambda by L is less than 0.01. Now we come to a very important property of fluid, viscosity. Viscosity. Now we come to a very important property of fluid, viscosity. Now this property, viscosity, you have heard, I think, since your childhood. But at the very beginning, to tell anything about viscosity, which is written in many books, you know, this will be a repetition to you because you have read it at school level also. I first tell you that viscosity is a property of the fluid, but it is manifested only if the fluid is in motion. So the viscosity property has got nothing to do when the fluid is at rest. So the concept of viscosity is realized through the motion of the fluid. So until and unless we analyze the motion of the fluid, we consider the motion of the fluid, the viscosity effect is not understood or manifested. So let us consider this way, that a flow of fluid in this fashion, that there is a flow of fluid where velocities are like this. Let us consider a flow of fluid. Let us consider, these are the flow velocities. Let us consider two axes. This is x axis, this is y axis. A situation of flow where the velocity u is in the x direction, which is a function of y. This type of flow is known as one dimensional flow, I will come afterwards, or parallel flow, where the flow velocity are in one direction, that is here in the direction of the x axis, and parallel to each other, that is the fluid velocities, which is function of y only. At any section, at any point, or at any region, we recognize the flow field, that the velocity of flow like this as a function of y. Now what happens, you see, at any distance y measured from this, at any distance y, that means at any location, we find the existence of a shear stress. That means a field of shear stress also exists along with this flow, which varies in the y direction. That means there is a flow which is varying in the y direction. That means the flow field, that is the velocity, is a function of y. So if a flow field is like this, always when the flow takes place, there will be a flow variation like that. This is a very simple case of one dimensional flow, where we will find out that there is a shear stress at each and every location in the flow field. So if you just see two adjacent neighboring layers at a distance y in an exaggerated view, let us here itself you make that at this we find out two fluid layer. They are adjacent layers, but it is drawn in a very exaggerated manner, two layers at that distance y. That means this is the distance y, where two layers. So what happens, the upper layer, this is the upper layer for example, because of its velocity in this direction with respect to the lower layer, tries to drag this lower layer or draw the lower layer in the direction of flow with a force F. Obviously, because with relative to this layer is moving in this direction, so it tries to draw this layer with a force F. These are two adjacent layers lying one over another. So this photograph, this figure which I have done in an exaggerated manner, that means the two layers are adjacent with each other, two adjacent layers touching with each other. So upper layer is moving with a higher velocity because of the typical velocity field that I have described, that u is a function of y in such a way that u increases with the increase in y. That means we assume the upper layer is moving with a higher velocity. That means relative to this, it is moving in this direction, so it tries to draw the lower layer in the same direction by giving a tangential force. By Newton's third law, the same force is given by this layer to the upper layer to retard the upper layer to a certain extent. So therefore, the mutual action between these two layers through these two tangential forces is to oppose the velocity variations. That means to equalize the velocity. It tries to accelerate it, it tries to retard it. However, in both the cases what happens, a field of stress is developed. Between the two layers it is balanced. But if you make an isolation, just like a free body diagram of this fluid body, we see that on this layer there is a tangential force or shear stress, that is the force by area, exists, which is the force exerted by the adjacent layer, which we have separated out in concentrating our idea as a solid body for free body for that liquid material. So this way we can conceive that a shear stress field is also developed in the fluid. That means if we write the shear stress tau is equal to F by A, as you know, if we define the area. So therefore tau is also developed. It was Newton first who due to Newton, who found out from experiments that the shear stress in this type of flow, consider only the simple flow, is linearly proportional, directly proportional to the velocity gradient du dy, and the direction in which the shear stress will act depends upon the direction of du dy or the sign of du dy. It is directly proportional to du dy. If du dy is going to be less, that means the curve becomes flat, so shear stress will go to a very low value. So shear stress is proportional to du dy, and this can be written as shear stress is equal to some proportionality constant mu into du dy, and this mu is the definition of viscosity. It is known as coefficient of viscosity, coefficient of viscosity, or simply we tell viscosity. Sometimes by viscosity we mean. So therefore this is an equation, very simple equation in case of one dimensional or parallel flow, where u is a function of y, that tau is equal to mu du dy, which means that shear stress divided by the velocity gradient at any location remains constant, and that constant is known as the coefficient of viscosity. That means this equation precisely defines the coefficient of viscosity. But here I have to say something which I can tell you will not find in no books, probably in almost all books. In my book you may find a line that initially this this relation is known as the Newton's law of viscosity. Let me write that. This is known as Newton's law of viscosity, Newton's law of viscosity. So I tell you one thing, that whenever this is asked what is Newton's law of viscosity, people tell that shear stress is proportional to the velocity gradient. It is so. In the very first phase of this course, we describe in such a way that this law states that the shear stress is proportional to the velocity gradient at the location. But this is not the generalized statement. That will be clear immediately afterwards, after a few classes. This velocity gradient, this is not the velocity gradient. Mathematically this is the velocity gradient. Physically this is not the velocity gradient. What is the physical entity of the velocity gradient? Shear stress, we understand, this is stress. This is the rate of shear strain. In a very special case, this will be shown afterwards in kinematics of fluids. For a parallel flow, when there is one component of flow u, which is a function of y, see, shear strain, rate of shear strain becomes simply the velocity gradient. That's why I will tell you to recognize this du dy as the rate of shear strain, rate of shear strain, rate of shear strain. So at the present moment you find this. Therefore shear stress, so Newton's laws of viscosity tells shear stress is proportional to the rate of shear strain, and the proportionality constant is the coefficient of viscosity, which is constant for the fluid and the property of the fluid. So therefore the velocity gradient in a very simple case, the way I explain, is the rate of shear strain. That is the rate at which the shear strain changes with time, the rate of shear strain. Now the fluids which obey the laws are known as Newtonian fluids. Now if I draw this in a graph du dy, let us see the abscissa is du dy, which is the velocity gradient in a simple case of parallel flow, or the shear strain, rate of shear strain, and this is tau. We see that for a given fluid it is a straight line and its slope is the mu, that is the coefficient of viscosity. So for different fluids it will be different. So this is known as Newtonian fluids, Newtonian fluid, where the stress is linearly proportional to the velocity gradient or rate of shear strain. This is known as Newtonian fluid. Now there are other fluids. Usually all engineering fluids, water, commonly encountered in our practice, air, oils, mercury, all are Newtonian fluids, where the shear stress is proportional to the velocity gradient or rate of shear strain, and the proportionality constant is known as viscosity, which is a property of the fluid. But there are other fluids which do not obey this linearity law between shear stress and the velocity gradient. These are known as non-Newtonian fluids. Non-Newtonian fluids. These are known as non-Newtonian fluids. Non-Newtonian fluids. So therefore, what are non-Newtonian fluids? Whose constitutive equation, that is the shear stress and the rate of shear strain or the velocity gradient for a simple case of flow I have explained, is not linear. This is non-linear. That is not linear but non-linear. You have understood? So these kinds of fluids are known as non-Newtonian fluids. And there are several fluids which are not very much usually encountered in engineering applications, but in process engineering, on biomechanics applications, the fluids are there which are non-Newtonian. For example, blood is a non-Newtonian fluid, milk is a non-Newtonian fluid. Polymer solutions, different polymer solutions are non-Newtonian fluids. Well, this is a vast subject. Non-Newtonian fluid itself is a very vast discipline. Polymer solutions, high molecular weight oil is a non-Newtonian fluid. Gelatin is a non-Newtonian fluid. Aqueous suspension of starch is non-Newtonian fluids. Ink is a non-Newtonian fluid. These are the non-Newtonian fluids. But non-Newtonian fluid as such is very simple. It is not so easy to tell that non-Newtonian fluids are those fluids where stress and rate of strain relationship or shear stress and velocity gradient relationship is not linear. That means which does not obey the basic Newton's law of viscosity, that tau is directly proportional to du. It is not sufficient because there are many complications. Non-Newtonian fluids in fact may be divided into two groups. This is beyond the scope of the class, but as I tell you, one is the time independent non-Newtonian fluid and the time dependent non-Newtonian fluid. In a time independent non-Newtonian fluid, the constitutive equation, it may not be linear, non-linear, but it remains invariant with time. It does not depend with time. But with time dependent non-Newtonian fluid, the constitutive equation, the functional relationship itself goes on changing with time. It depends upon the duration on which the force, external force or stress acts on the fluid body. So time dependent non-Newtonian fluids. Even for the time independent non-Newtonian fluids, there are various models given for its constitutive equations. But it is very difficult to give a generalized model which can describe the mechanistic behavior of all non-Newtonian fluids. So one very generalized model I gave you for non-Newtonian fluid is Ostwald D. Welle, Ostwald D. Welle, name of the scientist's model, which describes the behavior. It is one of the simple class power law models. They tell is m into du dy to the power n. It can be written in a different fashion to denote the sign of tau with du dy as n minus 1 separate with du dy, so that this tau, the sign of tau comes out with the sign of du dy. This is known as power law model. A class of fluids, many polymer solutions follow this power law model. Here m is known as flow behavior index, and n is known as flow consistency index. Consistency index. If you plot this power law model, we can get two curves. One is for n less than 1. This curve is n less than 1. There are fluids with power law model with n less than 1 and n greater than 1. This is known as pseudoplastic fluid, and this is known as dilatant fluid. Pseudoplastic and dilatant, these are two broad classes of very simple power law non-Newtonian models. Now again I tell here that This is the tau du dy curve, where this straight line represents Newtonian fluid whose slope is the viscosity of the fluid. Okay, I think time is up for today. I will discuss it in the next class. Thank you. Well, any query up to this, please? Good morning. I welcome you all to this session of fluid mechanics. Well, last class, if you recall, we discussed the constitutive equations of a fluid, which is basically a mathematical relationship between the shear stress and the rate of shear strain, which in a simple case we have shown it is a velocity gradient. Well, in a simple case of parallel flow where the velocity component takes place in one direction, it is the velocity gradient. And this class of fluids obeys a linear relationship between the shear stress and the velocity gradient known as Newtonian fluids. Okay, if you recall it, we see that the shear stress, look, if we consider a velocity field like this, if this be the velocity field, u is the velocity field in this direction, which is a function of y, where y is this direction, y. Then we have seen that tau at any location y, which is also a function of y, tau. We have seen that tau for a class of fluid is proportional to du dy, and this proportionality constant is, this is the velocity gradient. So tau is the shear stress, this is the velocity gradient in this type of problem, which is basically the rate of shear strain, which I will explain afterwards. So when we will come to fluid kinematics. So this constant of proportionality is known as viscosity or the coefficient of viscosity. And if we recall, we also discussed that if we show this in a tau versus du dy plane, then definitely this linear relationship is shown by a straight line like this. This is the the fluids which obey this law is known as Newtonian fluid, since the law is known as Newton's law, discovered first by Newton. Well, so constitutive equation is linear through origin. This is the Newtonian fluid, and the slope of this line determines the value of the viscosity coefficient. On the other hand, we recognize that there are a classes of fluids which do not obey this linear relationship, known as non-Newtonian fluids. And these fluids in general behave differently from this, and in fact no single model can be established for a class of non-Newtonian fluids. So we discussed a very simple power law model for a class of fluids, power law models for a class of fluids, which is very simple, that this relationship between tau and du dy bears a power law type relation, that means m into du dy to the power n, or we expressed it in a little different way, m into du dy to the power n minus 1 into dy, to give the sign of tau with this du dy. Here m and n are the constant parameters of these equations. These are known as, I told you in the last class, m as the flow consistency index, n as the flow behavior index. So these power law models are found by the scientist, his name Oswald D. Weyl model. Oswald D. Weyl model. So the fluids obey a power law model, a class of fluids with the values of n greater than 1 and less than 1. So if you plot the power law curve with the index n less than 1, the curve is like this, and with the n greater than 1, the curve is like this. Okay, difference is that the slope decreases in this case, tau divided by du dy, with an increase in du dy. In this case, when n is greater than 1, the slope increases with the increase in du dy. Slope means tau by du dy.
That means this slope decreases. So therefore you see these are the two curves. So the liquids or the fluids which follow this n less than 1 is known as pseudoplastic fluid, whereas n greater than 1 is known as dilatant, dilatant. But one interesting feature is that viscosity for any fluid is defined as tau divided by du dy. That means it is the ratio of shear stress divided by the velocity gradient in this case of flow, or we will see afterwards the shear strain, the rate of shear strain. That is the definition of viscosity. So if it does not bear a linear relationship, then the ratio is not constant, which simply means for any fluids whose constitutive equation is not linear, this ratio is not constant. For example, here if we see this ratio from this expression tau by du dy will be simply equal to m du dy, simple school level mathematics, n minus 1 tau by du dy here, which means we see that the definition of viscosity, if we write tau by du dy as mu, so you see mu precisely depends upon the velocity gradient. That means depends upon the flow situation. So therefore it is no longer a constant and ceases to be a property of the fluid. So therefore for Newtonian fluids only mu is a property of the fluid, but for non-Newtonian fluids mu is not a property of the fluid, since it depends upon the flow situation. Not only these are the properties, these parameters, flow behavior index and flow consistency index. So therefore this mu ceases to be a property of the fluid. In this case this mu is known as apparent viscosity, okay, apparent viscosity, mu is known as apparent viscosity. Now after this, okay, after this I will come to the definition of two very important things. One is ideal fluid. What is meant by ideal fluid? Ideal fluid. The simple definition of ideal fluid is a fluid whose viscosity is 0. That means we consider a fluid, hypothetical fluid whose viscosity is 0. But to be very frank, all fluids in reality have a viscosity greater than 0. There is no fluid whose viscosity is 0. But we consider an ideal fluid, define ideal fluid whose viscosity is 0. But at this moment definitely the query comes, why such an hypothetical fluid is defined and why there are certain laws and principles relating to ideal flow of fluids, because in your course curriculum I have shown that ideal flow of fluids, there is a chapter on like ideal flow of fluids. So at this juncture you just know this, that real fluids have viscosity greater than 0. So real fluids are known as viscous fluids. Now under certain situations of flow at very high velocities for viscous fluids, the flow field away from the solid surface can be very accurately generated by the principle of ideal fluid. And the theories and principles of ideal fluid from the common sense as it appears will be much simpler from that of real fluids which have viscosity, because the parameter viscosity is not coming into picture. So this is the reason for which theory of ideal fluid becomes so important. So at the present moment we may not know all those things, this is just for your interest. We can simply know ideal fluid is a hypothetical fluid whose viscosity is 0. So therefore if we see this curve, the abscissa represent ideal fluid. Why? If the viscosity is 0, this ideal fluid, whatever may be its flow condition or whatever may be its velocity gradient or rate of shear strain, whatever you tell, there will be no shear stress developed in the flow field. That means an ideal flow of fluid or flow of ideal fluid is devoid of any shear stress in the flow field. The shear stress will not be generated. Similarly, if we see the ordinate wheel represents ideal solid, this is ideal solid. Obviously this you know from your earlier knowledge that ideal solid is a solid where if you increase the stress to a very high value there will be no deformation. This is an ideal solid concept. So therefore the ordinate represents the ideal solid and the abscissa represents ideal fluid. Well, another class of fluids occur in nature, they behave like this, that a definite amount of stress is required to cause the motion. That means the flow takes place after a definite stress is applied to those classes of fluids or substances at the present moment I tell, and this stress value is known as the yield stress, tau E, yields tau Y rather, yield stress. This is known as yield stress, after which the flow takes place. And the relationship then between the stress and the velocity gradient may be of different nature, but a ideal relation will be a straight line, and these substances are known as ideal Bingham plastic. So Bingham plastic are those substances which requires certain yield stress to flow. You know, our paste and this type of liquid, they require this type of substances, they require certain minimum stress for the flow to take place. And in case of ideal Bingham plastic, the stress and velocity gradient or strain rate relationship becomes linear. But there is a little reservation for this class of substances to tell as fluid. This is because they don't start from the origin. You know that this physical significance of any curve, either linear or non-linear, to start from the origin is that under a infinite small shear stress, the liquid starts flowing. That means, or fluid starts flowing. That means fluid cannot resist even an infinite small shear stress under static condition.